Hello everyone. Welcome to this session on building resilient microservices using fault-tolerant design and patterns. First off, I just want to say that I really appreciate you taking the time to watch this session. My name is Anita Denadayalan. I'm a developer specialist solutions architect here at AWS, and I'm based out of Singapore. I work for the Developer Acceleration DEV5 team. In our team, we help our customers build secure, reliable, and scalable modern applications on AWS. You probably want to know what you can learn from this session today. I'll be talking about how distributed architectures require changes in the way we think and how network plays a key role in the design of the services. Then I'll talk about some of the commonly occurring problems in microservice architectures and the design patterns to resolve them. I will also talk about why you should use chaos engineering and AWS Fault Injection Simulator for testing the distributed applications. Today, I'll discuss the patterns in the context of a trip booking application, Travel Buddy. Travel Buddy lets you book hotel and flights. It's a monolithic application, typical 3-tier, web tier, application layer with a relational database. Monolithic applications have most of their functionality within a single process or a container. Internally, they can have multiple components, layers, and libraries. The application can have complex interactions, but they remain within a single process. But if a particular service, maybe you can think of the flight service here, has to be scaled, there is no way to scale just the individual service that's choking. The entire application has to be scaled to cater to the incoming requests. When releasing changes, entire application has to be regression tested and released. Let's imagine that our developers have been tasked to rewrite the code in the microservices architecture. Developers are now building microservices to create hundreds and sometimes thousands of small interconnected software components, and very often they are using different technology stacks. Here, we should remember that our developers are used to writing code for monolithic applications. They frequently disregard the unseen participant in the communication, the network. That's somewhat understandable, given that many middleware technologies have tried to make the developer experience of writing client code to be very close to that experience of calling a local function. So if the developers are not exposed to issues with network in their local tests with mock data, they are less likely to defend against them. So what happens when applications are written with little error handling or networking errors? If a network outage occurs, such applications infinitely wait for an answer packet, permanently consuming memory or other resources. When the services come back up, sudden and increased load might hit a running system, causing operations to return much slower than anticipated. Without timeouts or circuit breakers in place, this increase in latency will begin to compound and may even look like total unavailability to the system's users. Okay, let's look at the Travel Buddy application again. The different components are now extracted into microservices, and they are working together in an event-driven architecture. The services, they have their own databases. A call to hotel service may lead to multiple calls. Here, they can be flight service, payment service, before returning an output to the caller. Modern application architectures bring in a lot of benefits. They have smaller blast radius for changes. They have faster release cycles. They have less constraints with resources like CPU and memory, and they can scale on demand. You can also easily troubleshoot and deploy changes at a service level rather than at an application level. You can choose the best technology for each service. At the same time, now we have hundreds of services. There could be network failures, service delays due to peak loads. A single transaction may span different databases, making it harder to provide two-phase commit. So I'll be talking about some of the defensive programming techniques or patterns that you can use to design applications using microservices architectures. Imagine that you're calling an API to get hotel information from the Travel Buddy application, and there are intermittent network issues. If you are in front of your computer, you will probably be hitting the refresh button repeatedly until the call succeeds. But what if another process is calling this service? How are you going to make the same call again? A good way here would be to implement retries with backoff from the caller side. You can define the number of retries. Based on the response status, you can retry with an increased wait time between the calls. You're increasing the wait time because you're providing time for the network to recover. You may overload the network bandwidth if you retry too frequently. I've provided the code here in .NET, and you can choose to implement this in any of the programming languages that you prefer. The next scenario I want to talk about is service throttling. Individual services may be throttled when there are too many requests. Microservices communicate through remote procedure calls, and it's always possible that transient errors could occur in the network connectivity, causing failures also. Here, the trip service sends an event notification after processing. The reward service starts processing when the event arrives. This is an event-driven architecture, and the services are not aware of each other. So the retry logic cannot be implemented in the trip service code as it causes close coupling. A better solution here would be to use AWS step functions to retry and back off instead of embedding the retry in the individual services. So if a service call fails, the workflow can try again for a defined number of times with an interval and back off rate. In my example here, the workflow will wait for 3 seconds at first, and the back off rate is 1.5. So the workflow waits for 3 times 1.5 in the second try, which is 4.5 seconds. It will continue to the next step if it succeeds in one of the retries. So whenever there is service throttling or intermittent service failures, you can use the AWS step functions to retry the action. When multiple microservices collaborate to handle requests, one or more services may become unavailable or exhibit a high latency. If it is a synchronous call, entire application can become slow, and it would lead to poor user experience. A timeout in the recommendation service will propagate to the caller during synchronous execution. Imagine the operation invoking the service has timeouts, and it is waiting for the service to respond. The thread will be blocked until the timeout period expires. If there are many concurrent requests, these blocked requests may hold critical system resources such as memory, threads, and database connections. Now, the recommendation service team is trying to find the cause of the issue and fix it. But as you can see, the application has many users, and they continuously retry the operation. This can cause the entire application to go down. When faults are due to unanticipated events, it might take much longer to fix the issue. These faults can range in severity. They may cause partial loss of connectivity, or they could even lead to a complete failure of the service. In these situations, it might be pointless for an application to continually retry an operation that's most likely going to fail. Instead, the application should quickly accept that the operation has failed and handle this failure. The solution here is to use the circuit breaker pattern. This pattern can prevent an application from repeatedly trying to execute an operation that's likely to fail. In this pattern, there is a circuit breaker process that routes the calls from the caller to the callee. For example, in our Travel Buddy application, we can add a circuit breaker process between the trip and the recommendation services. When there are no failures, circuit breaker routes all the calls to the recommendation service. If the recommendation service times out, the circuit breaker can detect the timeout and track the failure. If the timeouts exceed a specific threshold value, the circuit is open. Once the circuit is open, the circuit breaker object does not route any calls to the recommendation service. Instead, it just returns an immediate failure. Meantime, as you can see, the recommendation service team is working on fixing the issue. The circuit breaker can periodically retry to see if the calls to the recommendation service are successful. If you see here, the service team is taking time to fix and the service is still not available. During the retry, if the call to the recommendation service succeeds, the circuit is closed and all further calls are routed to it again. Next, I'll be showing you a demo of the circuit breaker pattern using AWS step functions. This is the architecture for today's circuit breaker pattern demo. AWS step functions provides the circuit breaker capabilities here. I've designed the circuit breaker as a generic construct so that it's service agnostic. This is one of the ways of implementing the circuit breaker pattern. Trip service triggers the step functions workflow with the name of the service it needs to call through the circuit breaker. In this example, recommendation service. We can use the same circuit breaker with other services. For example, hotel service can call payment service with no code or configuration changes. I'm using Amazon DynamoDB here for storing the degraded service status, but you can also use an in-memory data store like Amazon Elastic Cache for lower latency access. In my demo, I'll first degrade the recommendation service by injecting timeouts and show you how the service status is stored in the DynamoDB table. Then I'll call this degraded service and show you how the service returns an immediate failure for subsequent calls. After a specified wait, the circuit breaker will call the degraded service again. I'm now in the step functions console. I've already created the step function workflow using AWS CDK, which you can use to create your cloud application resources using familiar programming languages. I'll click on the definition to see the state machine now. This is the circuit breaker state machine definition. It gets the circuit status from the DynamoDB database, checks whether the circuit is open or closed. If the circuit is closed, it executes the Lambda function. If the Lambda function executes successfully, the workflow exits without any error. If the Lambda function times out or returns error repeatedly, service is degraded in the update circuit status step with an expiry timestamp. The expiry timestamp is required so that the service call can be retried after a short wait time. So if the circuit is open, then an immediate failure is returned to the caller without executing the Lambda function. To get the circuit status, I'm using the AWS SDK service integrations to query the DynamoDB database. If the circuit is closed, then the query will return a count of 0. Otherwise, it will return a non-zero positive number. Execute Lambda step here provides the retry with exponential backoff capabilities. If this step times out after 3 consecutive times, the service is degraded by storing an item in the DynamoDB table. As I mentioned earlier, you can modify the data store to be an in-memory data store instead of using DynamoDB to get low latency access. So I've used CDK for .NET for creating the infrastructure. First, I create the roles for the Lambda functions and the step functions. Next, I'm creating the circuit breaker table in DynamoDB with the service name as partition key and the expired timestamp as the sort key. Then I'm creating the API gateway and the trip resource. I then integrate the trip service Lambda function to the API gateway resource endpoint. So the step functions definition I showed you just now, this is how I create it. I'm creating individual task states here and chaining them up together for the workflow. As you see here, I'm creating the state machine type as standard to have the visual workflow. If you're using this code in production workloads, use the state machine type as express to get a low latency execution. I'm storing the state machine ARN in an environment variable of the trip service Lambda function as I'll need this for triggering the trip step functions workflow from the trip service. This is the code for the trip service Lambda function. I'm reading the state machine ARN from the environment variable here. The function receives an input parameter object that contains the target Lambda name. I serialize the JSON input, trigger the step functions workflow here. The workflow will trigger the target Lambda function based on the service status. The step functions workflow is service agnostic. You can extract out the circuit breaker calling logic here into a separate DLL or Lambda layers and use it to integrate the circuit breaker workflow for any service. So far, I've shown you the state machine definition, CDK code for creating the infrastructure, and trip service code. I'll show the execution next. First, I'll make a call to degrade the recommendation service through Postman. I'm sending an extra parameter here to simulate the timeout. Recommendation service will recognize this flag and return a timeout. I'm clicking on send now. We will see this return status as 200 OK. Next, I'm going to show you the state machine execution where it retries a service call and then updates the service status in the DynamoDB database. The state machine is now executing the Lambda function. I've injected a timeout to degrade the service. So the Lambda function will be retried for 3 times as per my configuration. When it finally times out, an item will be inserted in the DynamoDB database, indicating that the service has been degraded. Let's now look at the DynamoDB table. The service name is the partition key and the expired timestamp is the sort key here. So if you see the output, recommendation service is now degraded. I'll now rerun the call and show you how the service returns an immediate failure. I've removed the simulate timeout and calling the workflow again. I'll click on send. If you see here, the state machine has returned an immediate failure as the service is degraded. It does so by checking the DynamoDB table, finds a record and fails immediately. The recommendation service is not called in this case. I'll call the recommendation service again now. So the state machine has now called the recommendation service and it has run successfully. The current time is greater than the timestamp of the item stored in the DynamoDB table, and the service is no longer considered degraded. I've used the AWS step function standard workflow for the demo as it provides the visual interface and it's easier for me to show and explain to you. But if you're planning to use this in production workloads, you can use the express workflow to achieve much higher performance and lower latency. There are situations when a single transaction can span multiple data stores. Basic principle of microservices is that each service manages its own data. So hotel service stores its data in its own database, flight service in its own, and the payment service can track the executed transactions in its own database. Anyone remembers storing blob data in relational database columns? How about a really long text? How many times have we converted data from one representation to another just so that we can store and track that information in the database? When using microservices, services can choose their databases that suits the need. In our example, hotel service uses Amazon Aurora, our relational database, and the flight service uses Amazon DynamoDB, which is our NoSQL data store. Payment service here, we can imagine, talks to an external payment SaaS. As I mentioned earlier, microservices communicate through events to indicate process changes. Imagine that a customer is booking a trip. This may include booking the hotel, flight, and making payment. You are seeing the happy path on the screen. There are no failures in the workflow, and the order gets place successfully. If you notice, this is an example of a distributed transaction with polyglot persistence. The transaction data gets stored across different databases, and each service writes to its own database. Let's imagine that there was a network failure and the payment gateway has timed out. So the last step in the workflow has failed. At the time of failure, the hotel database and the flight databases are already updated. But if you see the data, it is now inconsistent. Hotel and flights are booked, but the payment has failed. And there is no way to correct the data, and there are no options to retry the processes that have failed. In a relational database, we get ACID transactions: atomicity, consistency, isolation, and durability. If a transaction fails in a relational database, the transaction gets rolled back. But in distributed systems like microservices, two-phase commit is not an option, as the transaction is distributed across various databases. In this case, the solution is to use the Saga orchestration pattern. If any transaction fails in the workflow, the Saga orchestrator executes a series of compensating transactions that reverts the changes that were made by the preceding transactions. Let's imagine that a customer books the hotel when the flight tickets are almost full. Another customer secures the flight tickets and it becomes unavailable. As we all know, this can happen when multiple customers are competing to get tickets at the same time. In this case, the flight booking step will fail in the workflow. The orchestrator will now execute the compensatory transactions. It will run revert flight booking, remove hotel booking steps, and return the status as failed. As you can see, for every action that makes a change to the data store, there is an opposite action that compensates the change in the case of a failure. It's almost like Newton's third law: for every action, there is an equal and opposite reaction. A failure that happens in the last step, payment service in this case, will cause all the compensatory transactions to be executed before returning a failed state. The state machine makes it very easy for us to configure the compensatory transactions in case of failures. Here you can see how the Saga orchestration has been implemented with the Amazon States language. This shows the payment processing step of the Saga orchestration pattern. This can be easily extended to define the orchestration of a complex transaction. So to summarize, we solve intermittent network failures with retries in code, service failures with AWS step functions retry workflow, service delays and performance issues with the circuit breaker pattern, and distributed transactions using the Saga orchestration pattern. These are solutions to known problems. Once outages happen, it is easy enough because you can analyze things. Of course, you have to get the data, metrics, and traces to determine why it occurred. But how do you find issues that have not occurred yet? There are two types of complexity in software development. One is accidental complexity. Accidental complexity is generated by the developers themselves, like bad variable names or bad API definitions. The other is essential complexity. It is the complexity of the problem that we want to solve. It is the inherent complexity of the domains, so we can't remove it at all. The traditional way of tackling this challenge has been testing. But as distributed systems have become more complex, testing can only verify the known conditions in isolated environments. Answering questions like, is it what we expect? Is this the result of that function too? Those kind of questions. How can you test something you don't know yet? One way to deal with the unpredictables is using chaos engineering. By using chaos engineering, you can learn how the system behaves by running controlled experiments on your system. For distributed systems, even for a single request, many services are involved. So we need to aggregate information and visualize it to understand the system status and to trace the requests. This is what we call observability. And without observability, you don't have chaos engineering. You'll just have chaos. If you can't observe the behavior of your system, you can't learn from your experiments. This is the chaos engineering process. Firstly, we define the steady state. Next, we make a hypothesis and run an experiment by injecting faults. After the experiment, we check the system behavior and verify the hypothesis. If we see any difference between the hypothesis and actual behavior, we need to improve the system. Through iterations of this process, we can improve the system and gain confidence in the system's capability to withstand turbulent conditions in the production environment. Fault Injection Simulator is a fully managed service for chaos engineering. It helps you run experiments. Many similar services normally require the user to install an agent, but FIS does not. And you can configure a stop condition. So if experiments go wrong, you can stop them automatically. And is it really mandatory to do experiments in production? There are advantages of running an experiment in the production environment, but of course, it comes with blockers and risks. For example, if you're not familiar with some tools, there is a risk of making a mistake and you may unintentionally impact the users. So it's better that you start in the development or staging environment and familiarize yourself with the test tools. In some cases, it may be enough to do the experiments in the development environment. You join the AWS Summit to learn, and you can keep learning beyond the summit by using these training resources. Skill Builder is our online learning center that makes it easier for anyone from beginners to experienced professionals to build AWS cloud skills. We offer 500 plus free digital courses that can help you and your team build new cloud skills and learn about the latest services. And with that, I would like to thank you again for taking the time to listen to my session. I really hope my explanations will help you apply the patterns to your own distributed applications. I just have one final request for you, and that's to fill in the session survey. It'll only take a minute of your time, and it really helps me out to know what you thought of this session. I hope you enjoy the rest of the AWS Summit.